In this video, we're going to look at how to extend the chain rule to multivariable functions. So to begin, we're going to go back and revisit the chain rule of single variable calculus and look at it in the appropriate form to generalize it to multivariable functions. One way to state the chain rule for single variable functions is the following. So if y is a function of some variable u, let's call it f of u, and u in turn is a function of some other variable, let's call u g of x, then the derivative of y with respect to x, which I'm going to write in differential notation dy dx, can be thought of as the derivative of y with respect to u multiplied by the derivative of u, or the derivative of u with respect to x. Right? So this is not typically how the chain rule is written in single variable calculus. Usually it's written in the form y prime equals f prime of g of x multiplied by g prime of x, the derivative of the outside function evaluated at the inside function multiplied by the derivative of the inside function. But when we get to multivariables, that approach is really difficult to deal with. And so this differential notation is what is most easily generalized to the multivariable case. All right, so our goal in this and the rest of the videos in this section are to generalize this to all multivariable functions. And so we're going to do that in a couple steps. We're going to look at a couple cases first, of sort of special cases of functions. And once we see how it works in those particular cases, then we'll be able to sort of generalize and come up with the entire version, the big version of the chain rule that covers all cases. So our first case to consider for the chain rule is the following. We're going to have a z as a function of two variables. I'm going to call them u and v. And each of u and v are going to be functions of a single variable x. So I'm going to say that u is g of x and v is h of x. So the generalization part in this case is just looking at the function z. That's going to be a function of two variables, but u and v are both functions of one variable. In this context, it's easy to see that z is actually a function of a single variable x just by replacing u with g of x and v with h of x. All right, so g is a function of a single variable x, but it's still defined in terms of two independent functions, g and h. So the values of g and the value of h are completely independent of each other. And so because of that, what we often do is we give these variables names, like we typically do in functions. So we have z here, which is our dependent variable. Right, this is the value of z depends on the other variables in the problem. We have our variable x, which is our independent variable. Right, ultimately, this is the value we get to choose basically whatever we want for when we're evaluating this function. And in this case, we end up with two intermediate variables. Right, so these are variables that sit somewhere between the independent and the dependent variables. And in this case, this is a very natural place for this idea to occur, is when we're looking at compositions of functions in this sense. Right, and so we have these different variables, and in all the other cases, we're going to have all the other we're going to continue using these three words: dependent variable, intermediate variable, and independent variable in the same way. Right? So in this particular context, the function z is a function of a single variable. And so when we write down the chain rule in this case, we're going to compute a normal derivative using partial derivatives. Right? So our chain rule, we have to assume that all of these functions are differentiable. So I need f of uv to be differentiable, I need g of x to be differentiable, and I need h of x to be differentiable. All right, so if these are all differentiable functions in the appropriate context, then the derivative of z with respect to x, which is dz dx, all right, I can write d here instead of del because z is a function of a single variable x. There's no multiple variables in this context. This is going to be equal to del z del u, that is a partial derivative, multiplied by du dx. And then we're going to add to that del z del v multiplied by dv dx. So you can see that in order to find the variable of the single variable function z with respect to x, we actually need to compute partial derivatives of z with respect to u and v. And the key here is if you look at each of these two summands on the right side individually, this looks, except for the del, a lot like the chain rule for single variable functions. It's the derivative of z with respect to u multiplied by the derivative of u with respect to x. And then the same thing for v, dz dv multiplied by dv dx. Right? And so the key for the chain rule and multivariable functions is we're going to compute the derivative for each of the intermediate variables as we would with the chain rule, if that were the only variable, and then we're going to add all of those things together. In this case, the notation, we just have to be careful because some of these are derivatives of single variable functions indicated by a d, and some are derivatives of multivariable functions indicated by the del. One nice diagram that will be really helpful with the chain rule to make sure that nothing is forgotten is something called a tree diagram. And the way that a tree diagram works is that we're going to look at the three different variables, levels of variables that we just talked about, and indicate them in a tree. So we're going to start with the dependent variable, which in this case we said was z, so that will be on top. In the next level lower in the tree, we're going to list all of our intermediate variables. In this case, that's just u and v. All right, if we had 3 intermediate variables, we would list all three of them in this row. And then in the bottom, we'll list all of the independent variables, which in this case is just x. And what we can do is indicate an arrow downward from each variable to every variable in the row below it. So the dependent variable, which there will only be one of, will have an arrow pointing to every intermediate variable, and all the intermediate variables will have an arrow pointing to all of the independent variables, including if we had more than one. And so when we go through, each of these arrows represents a derivative. So the arrow from z to u represents del z del u, and the arrow from z to v represents del z del v. Right? Z is a function of the two variables u and v, so those are both partials. When we look at the arrow from u to x, that's a single variable function, so du dx. And the arrow from v to x as a single variable function, that will represent dv dx. Right? And so when we want to compute the derivative of z with respect to x, dz dx in this case, what we want to do is we want to look at every possible path from z, the dependent variable, down to x, the independent variable. And in this case, there's sort of two paths to go. There's this path on the left side, and there's this path on the right side. And so this tells us that to get the derivative of z with respect to x, we want to follow one of these two paths and then add them together. All right, and so that would result in del z del u multiplied by du dx. Then we add to that the other possible route down, del z del v multiplied by dv dx. And this is precisely the chain rule that was written on the previous slide. And so when we get to more complicated situations, this kind of tree diagram will become very useful to make sure that we have the correct derivative. So let's look at an example where we have to compute a derivative with respect to the chain rule. So let's say that z is equal to u cubed v squared, so it's a function of two variables. U is equal to x squared, and v is equal to x cubed minus 1. Okay. And we want to find the derivative of z with respect to x. Now, one approach you could take on this particular problem is to actually substitute x squared in for u and x cubed minus 1 in for v of this expression, and then explicitly write z as a function of one variable and then differentiate it using Calculus 1 material. But while you could do that, there are cases where the chain rule is absolutely necessary, where it's very difficult to compute z as the function of x. And once you compute it, then you have a very, very difficult function to differentiate. And so we're going to use this, just a simple example, to illustrate the chain rule. So that's what how we're going to approach this problem. So the first thing is to apply the chain rule. So dz dx we know is going to be del z del u multiplied by du dx. And we're going to add to that del z del v times dv dx. All right, so we just need to compute all of these quantities. Right? And this is where the partial derivatives come into play. So del z del u is going to be 3u squared v squared. Du dx is going to be 2x. Del z del v is going to be 2u cubed v. And dv dx is going to be 3x squared. Now in this case, at this point we can go ahead and substitute in the values for u and v, and then we'll be done. So this will be 3 times u squared, so that'll be x to the 4th. V squared would be x cubed minus 1 squared times 2x, plus 2 times u cubed, so that'll be x to the 6th times v multiplied by 3x squared. Right? And if our goal is just to find the derivative of z with respect to x, notice that this works. This is a function here that I've written in terms of just x, and it certainly would work in any context we would want. If we wanted to compute this first, evaluate it at some way, we could. Now, it's not required, but if you wanted to simplify this, if this is something, I know sometimes people really want to simplify things whenever possible. It turns out this is 6x to the 5th, x cubed minus 1 times 2x cubed minus 1. All right, so this is, you factor out the 6x to the 5th and the x cubed minus 1 from each, and you're left with the 2x cubed minus 1. And so let's look at one more example of a chain rule problem like this. Right, so let's say we had a function f of x, y, function of two variables, given by just the product of x and y. X is going to be the sine of 2t, and y is going to be the cosine of 3t. All right, so this is our setup, our function f of two variables, and each of those variables a function of a third variable t. And so what we want to do in this case is we'd like to find the value of f prime of t at the points where t equals 0 and t equals pi over 6. Okay. Now again, you could take x and y, you could put them into this function f and form a function of one variable and differentiate. You're going to have to use the product rule and chain rules there. But the chain rule of multivariable calculus really helps us do this in a little bit of a simpler way. So in this particular case, the chain rule tells me that f prime of t, the derivative of f with respect to t, is going to be del z del x multiplied by dx dt plus del z del y multiplied by dy dt. And these are all quite easy to compute. Del z del x is just y. So I have y times dx dt. Dx dt is just going to be 2 cosine of 2t. And then we're going to add to that del z del y, which is x, multiplied by dy dt, which will be negative 3 sine of 3t. All right, so this is our function. And again, we could put in y and x if we wanted to. But in this case, it's not necessary. We know when t is equal to 0, right? We know the values of x and y there. We know that x is going to be sine of 0, which is 0. And we know y is going to be the cosine of 0, which is 1. So we know x is 0 and y is 1. And so f prime of 0 is simply going to be 1 times 2 times the cosine of 0 plus x, 0, times negative 3 times the sine of 0. And this ends up just being equal to 1 times 2, which is 2. Now, when t is pi over 6, right, we see that x is going to be the sine of 2 times pi over 6, so the sine of pi over 3, which is square root of 3 over 2. And y is going to be the cosine of 3 times pi over 6, so that would be the cosine of pi over 2, which is 0. And so f prime of pi over 6 is equal to 0 times 2 cosine of 2t, so that of course is all 0, plus square root of 3 over 2 times negative 3 sine of pi over 2. Right, sine of pi over 2 is 1, and so this ends up being negative 3 square root 3 all over 2. Okay. Now again, you could have from the very beginning formed function f as a function of a single variable t and did the derivative, and we would have done basically the same calculations, just set up a little bit differently here. But for more complicated functions, the chain rule can often be the more elegant approach.